Hey everybody. So today we're going to talk about circuit reduction and what we call the divider circuits in circuit theory. Okay. So this should be your second lecture in a series of many. At this point, you should know what sources are, the types of sources, Kirchhoff's voltage law, Kirchhoff's current law, power, passive sign convention. All right. You should know what a short circuit is, an open circuit is, and you should also know what a resistor is and its fundamental current to voltage characteristic. Basically, V equals IR. We call that Ohm's law. All right. So now that you know all of that, it's time to learn some more stuff. But at this point, you haven't really had to do much more than KBL, KCL, and then combine the two equations with Ohm's law, as you need to do them. But what happens when you have a bunch of resistors in your circuit? All right, let's say you have more than 3 resistors in your circuit. Well, you don't want to always have to be able to do V equals IR like 3, 4, 5, 6, 7 different times. It'd be really nice if instead of using 7 resistors, you could just combine all the resistors, maybe into 1 or 2 resistors. Okay, so that's going to be the whole idea behind circuit reduction. The whole idea behind circuit reduction is you're going to shrink your circuit so that it can become easier to solve. So that it is easier to solve. Okay. So that's literally all we're doing here. We're basically trying to come up with shortcuts to solving our circuits for the cases where we get medium to large scale circuits. All right. In order to do that, we're going to have to understand the connection types. But before we even do that, we're going to I guess in the scope of us learning connection types, we'll talk about resistor reduction. There are 3 aspects to circuit reduction as we know it. Technically, there are 4, all right? But the 4th piece you're going to learn as its own, topic, all right? The first thing we're going to learn is resistor reduction. The second thing we're going to learn is what we call the voltage and current divider circuits, which aren't really a reduction, but it's basically still a shortcut. So we like to teach it in this section. And then after that, we're going to learn the source transform, okay? So let's start off with resistor reduction, all right? And in the scope of resistor reduction, we'll talk about how it all works. Resistor reduction. So I'm going to say I like this. There are 3 ways that you can combine. There are 3 fundamental connection types, is what I'll say. There are 3 connection types between elements. Okay. We have what we call series, parallel, and neither. Okay. So 1 is series, 2 is parallel, and 3 is neither. Okay, and you're going to have to know how to identify these. Basically, all I'm saying is there are 3 ways you can stick pieces together in a circuit. That's all the statement is saying, all right? As long as you know the 3 ways, each way has its own rules associated with it. Really, there are 2 ways that you need to know. Neither is the case where you're kind of stuck. So if there are 3 ways to connect all elements, then there are 3 ways to basically connect resistors. Elements can combine with other elements of the same type. What that means is resistors can combine with other resistors. Voltage sources can combine with other voltage sources. Current sources can combine with other current sources, and they all have their rules on how they can combine. All right. So what we're going to first learn is the series connection. Okay. This is what a series connection looks like. But don't let your eyes trick you. So let's say we have 2 resistors in series. I guess we have 2 resistors, R1 and R2. A resistor is defined to be in series if you spontaneously generate a current, I, is going to pass from one to the second one without ever branching off into multiple pieces. Okay, so I between R1 and R2 is the same. All right, that's what it means to be in series. They share the same current. I gotta make this line a little bit thinner. Oh no, there we go. They share the same current. That's what it means to be in series. A lot of people like to say, oh, It's what you get whenever you have the two elements sharing one node. So let's say we call the node between them C. This is not really a good way of understanding series. All right. The best way of understanding is if you generate a spontaneous current and it travels and you have it propagating, if it does never branches off into any other elements, then they're all in series. Okay, they're back to back. All right. So the reason I don't like that is because let's say I had an element like this and I added it here and I called this right here C. Okay, well, R1, R2, and R3 all share C, but R1, R2, and R3 are not in series, because if I were to draw that current, it's going to come like this, and then also some of it's going to go that way. The moment that current branches off, automatically takes me away from the series connection. All right, so I don't really like the nomenclature of they have to share one node. I don't think that's really accurate. This is the best way of understanding series. Okay, so series means that you can, these are back to back, and also means that they share the same current, and that consequence is really, really fantastic. But this is basically the connection that's associated with current. All right, everything I like to say is associated with either voltage or current. Every phenomenon in circuit theory, the series connection is a connection that's associated with current. What I can say is, if I have resistors 1 and 2 in series, they conglomerately behave as one resistor, what we call the equivalent resistance, Req. Okay, in this case, it's between A and B. Well, that Req is going to get the same exact current. So if current is passing from A to B, this is going to get the same current that these two had. All right, and all I have to do is understand what the equivalent resistance is equal to. Well, when it comes down to a series connection, the equivalent resistance is equal to R1 plus R2 plus however many resistors are actually in series. Turns out series and parallel does not have to be a connection between just two. It could be as many resistors as you want. As long as I have, if let's say I have 99 resistors, if all 99 resistors are back to back to back to back to back to back, they're all in series with each other, and the equivalent will be 1 plus 2 plus 3 plus 4 all the way till however many I have. Okay? So that is the series connection. All right? Next, I'll talk about the parallel connection. So that was series. Let's talk parallel. Parallel is definitely the harder of the two connections to understand. All right. So here we go. Here's a drawing of parallel. And when I say do not let the drawing fool you, don't always look for something that looks just like this. Don't always look for something that's just like that. All right. I've drawn this so you can get a visual, but all of your series connections are not going to look like this. All right. You're going to have to use the fundamental ideas of, oh, is the current ever going to branch off? Oh, is the voltage ever going to, or are these between, different nodes or whatever, how we're going to define parallel to define our stuff. Okay. So let this be R2, and I guess this will be R1 then, and they'll be between nodes A and B. Okay. The parallel connection is defined as such. If ever you have a resistor or an element and it's between A and B, anything else between A and B has to be in parallel with the original. So in this case, because R1 is between A and B and R2 is between A and B, they're both in parallel. Okay. Now, another way to think about the parallel connection. That was one definition. The second definition, because there are two ways to understand it, is, I guess not a definition, but a consequence of the definition. Use the A and B, basically whatever's between the same two nodes has being parallel. This is a consequence of that. Voltage sits between nodes. Okay, there's a voltage between A and B. And since everything is between A and B, everything has to have that same voltage. Everything in parallel shares the same voltage. So basically, if the series connection is the is the current connection, then the parallel connection is the voltage connection. Okay? Current connection, voltage connection. All right? And you got to understand the consequences. So the consequences are which connection type it is, and then how to understand, if it's in its connection or not is how do you read it. In this case, R1 and R2 are back to back. There's no forks in the road basically between them. In this case, R1 and R2 are between the same two nodes. That's how you define series versus parallel. And it's not just for resistors, it's for everything. All right? You can put voltage sources in series, you can put current sources in series. I don't advise doing that actually. You'll never see current sources in series. You can put voltage sources in series and you can put current sources in parallel. Technically, that's how it works. All right. And there'll be an example where we actually dictate how do you add current and voltage sources. All right. So don't worry about, us not talking about them right now. Right now, I want to talk about how we reduce resistors. All right. So if you have two resistors in parallel, all right, between A and B, all right, they're going to have some equivalent resistance. They're going to have some sort of conglomerate behavior, where in this case, the voltage on the equivalent resistance is the same voltage on both of them, and I have to have a mathematical representation of what they'll behave as. Now, in series, the equivalence is 1 plus 2 plus 3 plus yada, yada, yada. But in parallels, it's the inverse. 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus yada, 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 yada. However many resistors are side to side, how many resistors are in parallel. I could have 99 resistors between A and B. They're all in parallel, okay? Now, here's a special note about the parallel connection. If ever you have two resistors in parallel, you can just say this. Req is R1 times R2 over R1 plus R2. This only works for two resistors, okay? A lot of people misunderstand this. Okay, a lot of people think, oh, if I have, oh, that was bad. A lot of people think, oh, if I have 3 resistors or 4 resistors, I could use 1 times 2 times 3 and 2 times 2 times 3. Nope, doesn't work like that. You have to do 2 by 2 by 2 if you want to crush them down like that. So you have options. If you have many, you could just use this equation, all right? Or if you have a bunch, let's say you have 4 resistors, you combine 2, you combine another 2, all right? So then you go from 4 to 2, and then you combine the final 2, and you run this equation 3 times basically. So you do this over and over and over until you crushed it down to however many elements you want, all right? But remember, this equation right here only works for 2 resistors, okay? So there we have it, the series connection, the parallel connection, the consequences of what it means to be in series and parallel, all right? If you're in the neither connection, then you are neither series nor parallel, all right? Examples of the neither connection is the standard T, all right? So let's say this was node A and this was node B. Well, let's say this is R1, R2, and R3. R1 and R3 are not in series, all right? Because R2, if you were to draw a current, it would come in here and it would have to break off. Because of that, they're not in series. They're not in parallel, because if this is A and this is B, then this right here would have to be something like C. This is between A and C. This is between A and B. This would be between A and D. Because none of them are between the same two nodes, they're not in parallel. Thus, they must be in the neither connection. If you're dealing with resistors in the neither connection or elements in the neither connection, you can't do anything with it, at least not until I teach you some other stuff, all right? So for now, you're either in series or parallel. If you're in a neither connection, then you can't deal. All right, you're going to have to just do KVL and KCL. You're not going to be able to crush your circuit down. All right, so we're going to stop here, and then in the next few videos, we'll talk about the voltage divider and current divider circuits, and then we'll talk about the source transform. But basically, with the resistor reduction, if I have 8 resistors in a circuit and I want to focus on finding the voltage or current through one of them, I can turn the other 7 resistors, the ones that I don't care about, into one resistor, and then I'll basically be dealing with the circuit now with 2 resistors instead of 8, all right, which is a lot easier to deal with. All right, so we'll stop for here, and then we'll come back with the voltage and current divider.